Adding vectors graphically using the tail to tip of the parallelogram method can sometimes be tedious and inaccurate because we have to use protractors and rulers. We have to be very neat. Now this is a very inefficient method, and another more efficient method exists, and this is known as resolving our vectors into its components. In other words, instead of graphically adding vectors, we can add vectors by adding the components of the individual vectors and then using a formula, as we'll see in just a moment, to find our magnitude as well as direction of the resultant vector. So let's suppose we have the following two-dimensional vector. So here we have our y-axis and the x-axis. So we can resolve this vector or break this vector down, v, into its components by drawing a vector going along the x-axis, beginning at the origin and ending at the same position, at the same x value as this original vector, and beginning at the origin and ending or going up along the y-axis and ending at the same height as our original v vector. So this is known as our vector component along the x direction, vx, and the vector component along the y direction, vy. Notice these two components are exactly perpendicular at a 90-degree angle to one another. In other words, if I take this vector component vy and shift it over along my x-axis to this point and connect my vx tip and my tip of my original vector v, I get a triangle. And now I can use my a squared plus b squared equals c squared formula, the Pythagorean theorem, to find what my final v vector magnitude is. In other words, v vector squared is equal to vx squared plus vy squared. So I take the radical of both sides and I find that my absolute value, the magnitude of my v vector, is equal to the following formula: vx squared plus vy squared, and take the radical of the whole sum. Now, this absolute value simply refers to the magnitude of the vector and not the direction. Now, if I look at the following triangle, I notice that if I know the angle between this vector and the x-axis, my original vector and the x-axis, I can use my trig functions, my trigonometric functions. So let's go over here. So let's take this and we draw it, and let's say the angle between my vector v and my x-axis is theta. So the sine of the angle theta is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent side. So let's rewrite the opposite hypotenuse in the following way. So my opposite is my vy, my component along the y-axis. And then my hypotenuse is simply my magnitude of my original v vector. So if I rearrange this, I see that if I know my angle and I know my vector, my magnitude of my original vector, I can find my y component in the following way by using this formula. Vy is equal to sine theta multiplied by the magnitude of vector v. Now, in the same way, cosine theta is equal to adjacent vx divided by v. So cosine of theta is equal to vx divided by v. I bring v to this side and I see that if I know my magnitude v and I know my angle, I can find my magnitude of the x component vector. Finally, I see that tangent of this angle is equal to vy divided by vx. In other words, if I know my value of vx and my value of vy, I can find what my angle is. In other words, I can find what my direction of this original vector is. So these formulas, these two formulas with the stars, are equations that will give us the magnitude of the vector v. And it's given by this formula that we found earlier. So our magnitude given by the absolute value of v is equal to the radical of vx squared plus vy squared. And we just said vx squared is given by this formula and vy squared is given by this formula. So we plug vy sine theta times v into this component, and we plug in cosine theta v for this component, and we see that another way of writing this formula in terms of just v and the angle is shown here. Now, this equation will give us the direction of our vector. So, one of the equations gives us the magnitude, and the second equation gives us our direction. Remember, a vector has both direction as well as magnitude. So, let's look at the following example. Let's suppose we have the following two vectors. V1 that has an angle of 30 degrees along the x-axis, and V2 which has an angle of 60 degrees with respect to the x-axis. Let's say the magnitude of V1 is 10 and the magnitude of V2 is 15. Now, I want to add these two vectors up without having to use either the tail to tip or the parallelogram method. I want to use the component method. So that means I have to break down each one of these vectors into its components. So I find the x component of V1 and the x component of V2, I add them two up. Next, I find the y component of V1 and the y component of V2, I add them up. And finally, I use this formula to find my magnitude. So, Vx1 plus V2x gives us, so we know that V1 has a value of 10, and if we're looking for the one for the component along the x direction, our formula is given here. So Vx is equal to cosine theta v. So cosine of the angle 30 multiplied by the magnitude 10 plus cosine of 60 multiplied by 15, the magnitude of V2, gives us the component of the combination of these two vectors along the x direction. And that's about 16.16, so we'll say it's 16. What about along the y direction? So, the component along the y direction of V1 is sine of 30 times 10. The component of vector 2 along the y direction is sine 60 multiplied by 15 as given by this formula. So the resultant component of the combination of these two vectors along the y direction is approximately 18. Now we use this formula, so the total along the x direction and total along the y direction, we square them, we add them, we take the radical, and we get our magnitude of our vector that we get when we add these two vectors, V1 and V2. So, 16 squared plus 18 squared, take the radical, and we get approximately 24. So 24 is the magnitude of our vector. To find the direction, we simply take our Vy divided by Vx, and that will give us the tangent. Then we take the inverse function of our tan, and we get our angle.